Welcome, everyone, to GAM402, Turbine, a microservice approach to 3 billion game requests per day. I'm Ramesh McCullough, staff software engineer at Turbine.
I'm William Day, a senior software engineer on the WBG Play team.
And I'm Evan Pipo, the engineering lead for the mobile game platform server team.
So what to expect from this session? We're going to talk a bit about handling gaming workloads on Amazon. We're going to share a bunch of personal experiences from a AAA multi-platform game launch. Unfortunately, due to studio policy, I'm not allowed to name the game. And then also just to unpack this a little bit for anybody that's not in the game industry, AAA is sort of just a way to denote like a larger budget or production, kind of like calling a movie a blockbuster. And then multi-platform, in this case, we're talking about console, so Xbox and PlayStation. We're also doing PC, mobile, iOS, Android. We're going to overview our new containerized service platform running on Coreos and AWS. And then we're also going to talk a little bit about scaling MongoDB and some of the challenges and strategies we found for some specific issues that we hit that were a little more specific, I think, to handling gaming workloads. So this talk is going to be arranged into a handful of specific challenges. I just want to overview them quickly for everyone just so it makes sense when we're going through. So we're going to talk about managing multiple games on AWS. And part of what we're talking about isn't necessarily provisioning, but like how do you actually structure things for like a multi-studio, multi-tenant type setup. Or talk about scale as a challenge, like when you don't know what to expect and how you can sort of use some of the features of Amazon to make that something a little saner that you can handle. Also, picking your battles. There's a number of things going into this launch that I mentioned that we could have done, and we were very specific about what we chose to solve and what we did not. And we're going to go through a little bit about what we did choose to solve, and that's where we'll start talking about the containerized service platform as well. Like I said, MongoDB at scale. And the last one, staying up through launch. I think everyone that's familiar with games or the gaming industry is well aware of launch time outages and how common they're becoming. And so we'll share some of the strategies we found to help control what was happening a little bit. So quickly, a little bit about us. We are Turbine. We've been around for a while, founded in 1994. We were purchased by Warner Brothers in 2010. We've been doing this for a while. I don't know if people remember Asheron's Call. It was a very early MMO, so we're very experienced with both large properties as well as lots of online real-time games at scale. We do work with large properties. Lord of the Rings is a big one, Dungeons & Dragons, DC Comics. And we're about to launch our first mobile game, Batman Arkham Underworld, and we'll be talking a little bit about that as well. But across all of Warner Brothers, Turbine actually does quite a lot of stuff. We work with a number of different games with a number of different platforms. I just want to walk you through quickly what those are. We have the WB Play game stack, so a customized cross-platform, cross-studio game backend for analytics, and that's something that Will's going to talk about. We also have the mobile game platform, so the next-gen game backend specifically geared for the Turbine mobile games, and that's what Evan's going to go over. But additionally at Turbine, we also have a pretty significant analytics platform for crunching game data across all of the Warner Brothers interactive organization. We also do the WB Play identity stack, so that is a lot of identity, account management, and e-commerce. But we're really going to be focusing on the first two. That's going to be a lot of what we're talking about. So just to overview those a little bit, right now they're going to be powering Batman Arkham Underworld and this unnamed AAA multi-platform game. And that game is going to be kind of the context of, or that launch will be the context of everything that we're talking about. How we got ready for it, how we handled things that happened, how we handled triage and all that stuff. And a little bit of an overview of what they are providing for those games. It does stuff like anything you need to online enable your game. So authentication, profiles, matchmaking, match history, guilds, cross-platform unlocks, feeds, the whole, everything you need. And so since we are Turbine, we've been doing this for a long time. We do have data centers. We do have existing infrastructure. So why do we want to go to AWS? I know that's not something I'm going to super focus on because I'm sure everyone here is pretty familiar with it. But some of the reasons we had for taking this specific launch out there had some concerns about data center capacity. We do have multiple data centers, but we're not used to console, PC, and mobile all at once. So there's a sort of traffic profile that we weren't super familiar with. Related to that, it's an unknown infrastructure footprint. We weren't sure if we would actually be able to scale within our own existing infrastructure. So we wanted to make sure that we had the best chance of actually being able to do that. Additionally, since we've had a platform running for a little while, we don't have a lot of great automation tools for our physical infrastructure today, and we didn't have the time to get there before we had to launch. So, that was really helpful. Gaming workloads are very bursty. We see more traffic on day one than you see basically ever after that. So going from 0 to everything is a non-trivial challenge. And then, of course, just multiple availability zones. You can build in multi-AZ without any extra real work. So when we run multiple data centers, we still have even more presence that we can leverage. So I'm going to take this right into our first challenge. How do we actually set up AWS? It's something more, like I said, more fundamental than using an API to provision servers. We need to support multiple games, multiple studios with multiple environments and multiple teams. That's a lot of stuff. And we weren't really sure how to structure our accounts up front to make sure that we don't have anything clash. One game, because we work across studios, can't affect another. And there's a lot of ways that it could, specifically like service limits and accounts, or just the things that can happen when you're running a lot of environments with a lot of people that have to access it. And of course, access control, we need to figure out how we wanted to solve that. And then part of working for Warner Brothers is they have some rules about how and where we're allowed to store our source code. So we need to be able to access some centralized services. We weren't able to use some of the public cloud services out there. So working with our solutions architects, we actually settled on multiple AWS accounts. We have one account per game, so every title gets its own account with its own service limits. We set up a VPC for environment. We tend to be 5, dev, cert, QA, prod, perf. And we have a separate account just for core services. Some good sides, service limits can't clash. So if we have a major scaling event in one game, because you never know, it can't prevent a major scaling event in another game at the same time. And that's extremely important when you have to work with multiple large projects at the same time. There are some cons, though. It's a lot of management. There's a lot of stuff. You really need to automate it. But in the end, we felt that if quantity was the thing that we were really concerned about, that's an orchestration problem. And we can solve orchestration problems. And unfortunately, that's not even actually the exact topic of this talk, but I am going to share a few things about it. And just to kind of visualize what this looks like. So we have our one ops VPC. We use VPC pairing, set up a second account. One note, each of those VPCs, they're actually all separate VPCs. We just sort of condensed the slides to make it a little more clear. But they can talk over VPC peering. It's all private IPs. It makes it really easy to discover stuff. You can use Route 53 private zones to direct traffic as you need. Very specifically, also, we're leveraging the kind of inherent blast radius of a VPC. So by choice, dev can't talk to prod, can't talk to perf. We could allow it. We elect not to. For a number of reasons, blast radius. You can't misconfigure something to talk across accounts. A prod app can't talk to a dev database. That's important. And we get that for free, which is really nice. Set up another account. Basically identical, VPC peering. And very, very specifically, they can't talk across. Again, could, but we don't want them to. And that gives us a lot of the isolation that we need as a company to run a number of major titles simultaneously. So one issue, that's probably not new to a lot of anybody that's set up an actual network before, but running that centralized VPC, you have a route table. Route tables need to have unique entries to route to every other VPC. So, we had to pre-provision that at first, and we had some organic growth early on that actually caused a problem. There's a little bit of an overview of what we did. We had 1/20 per environment. We provisioned 5 environments up front. We divide it into 3 public and 3 private subnets. We can put our public ALBs in the public subnet, and we can use private resources. Most of our resources live in a private subnet, so they're just nicely isolated from the internet in general. And we also came up with a bit mask early on to just pre-compute probably the next 5 years of our growth. And we can look at NIP, we know what environment it's in, what region it's in. And that was actually really helpful. So we just have it mapped, and we're good. So let's do a little bit of an architecture overview of what we're going to talk about as far as the core systems and platforms that I mentioned earlier. 10,000 square foot view, very, very high level. You'll see we have the WBG stack on the left, MGP stack on the right. And a lot of our talk is going to be going through our reasoning for why we actually needed to add that fork on the right and how that was actually extremely valuable for us, and some of the issues that it let us not even have to worry about. So I'm going to hand over to Will, and he's going to talk about the WBG stack.
Thanks, Romy. So I'm going to talk about this left fork here, the WBG stack, and how we dealt with scaling this up in prod. This is a pretty old code base going back a while. It's primarily the game backend and analytics data. It's a monolithic code base that goes back to 2006. It's supported a lot of games. It's evolved a lot over time. It's seen a lot of dev teams, a lot of different games. It's Python on Linux, pretty standard. It's using MongoDB and Redis for storage. And because it's evolved over time, it has a lot of code inside to handle different binary message formats for different games and different environments. It's got SDKs out in the wild for different consoles, different mobile games over time. And the configuration of it was a lot of Chef Solo. So we had a lot of things to think about with this stack. Conceptually, it's pretty straightforward. We have a proxy layer that's handling traffic. It hands it into RabbitMQ. Side note for anyone who doesn't know, RabbitMQ is a message bus that supports the AMQP protocol. It can route messages from the proxy layer to the services registered with the bus. And then all of the services that are attached to RabbitMQ are handing that, doing that work in a shared data layer, which in this case is MongoDB. All of the services are sharing the same data layer. Well, how do you take something conceptual like that and run it at scale for a game? Well, we need high availability. We want to isolate it from the public internet. We're going to have to balance load across the proxies and the services. We're going to need to scale all the application components. We're going to have to scale MongoDB. We're going to need to automate our configuration management. And we're going to need Redis to be highly available. This is a lot of things to care about for this stack. But we used a lot of the Amazon features to sort of cross things off the list that we had to care about. High availability, we can use AZs. We can use a lot of the Amazon features with APIs just to make that not a problem for us to care about. We put it in VPCs to get it isolated from the public internet, also something we don't have to care about. Use ELBs for load balancing, also not a problem that we have to think about. We use baked AMIs, so we had to configure things once and then not automate configuration in prod. And we used Elasticache for highly available Redis. We're down to 2 problems that we have to solve at this point. So this is what it looks like when we implement it. And you're not meant to actually take this all in, but what you're meant to take in is this is a lot of stuff to care about. And we were able to use a lot of the Amazon APIs to focus down on the things we actually want to care about, which is the application stack. We still have a lot going on here. We have, groups of proxies talking to RabbitMQ in different AZs, the services registered in different AZs and subnets. We still have a lot of Mongo to care about. We still have a lot to scale. So what's the big challenge with scale for gaming, in this case, where we're doing a multi-platform launch? Well, day 1 patches are a thing. We have game clients being finalized close to launch. We have a lot of different builds of clients that are coming in from different teams all over the place. Different platforms are handling the game in different ways, using the APIs differently in the different clients. The different ports for the different clients are being handled by different studios. So we have a lot of variation going on in how the one game is going to use the same stack. So it's really hard to establish metric baselines to understand how to scale everything when you have this much going on and coming in this hot at launch. We have to put bounds on stuff. So first thing we did for scaling is said, what are the absolute bounds of things that we'll need? One thing, ELB pre-warming, it's a thing, do it, you need it. We also set what we thought were crazy high EC2 instance limits. For note, at peak, we had 88 C4 8x larges and 72 R3 8x larges. So these limits, we really needed to bump them up, not really easy to do. And we had about almost 200 terabytes of GP2 allocated for the game, and just followed the standard practice of randomizing your S3 buckets to scale out the performance of those. Well, how are we going to understand how the game is working once we launch it? Pre-production, we had a lot of metrics from load tests and from clients, but the metrics we were getting were external metrics. They were coming from the load test clients. We were looking at them in Amazon CloudWatch. When we launched, we weren't going to have that stuff. We weren't going to be able to get the metrics from the actual game clients. So pretty late in the game, we went through and added instrumentation right into the actual back end. We did this sort of what's standard practice at this point, use statsd to send it to Librato. Statsd is just a protocol for sending metrics. Librato is a hosted metric collection and graphing solution, basically hosted graphite. But as I said, really hard to get baselines and figure out what are the actual things we want to measure. So we just measured everything. So what's our level of operational complexity for this? We've already eliminated a lot of the things we have to care about and limited our scope down to the application stack. But we still have 9 scalable components just for the app layer. We still have to figure out how to scale and make RabbitMQ highly available across multiple AZs. Do we want to use federation? Do we want to use shovel? How are we going to do this? What are the failure modes going to be? We need to be able to shard and scale MongoDB. And we need to be able to distribute Redis load. So we use Twem proxy across Elasticache to get rid of that. We're not going to talk about that again, but it worked out well. We've got this diagram here, a lot of stuff to scale, a lot of unknowns. We took a step back and tried to think about how can we take this and focus on the key bottlenecks. So we knew that RabbitMQ was everything has to go through RabbitMQ. Everything eventually ends up at Mongo. So we have to be able to scale those when we need to. Everything else, the proxy, the services, they're all just in auto-scaling groups. We can scale them up and down as we need. But there's more mechanics to scaling RabbitMQ and more mechanics to scaling MongoDB. So we took the application stack and figured out a way to make it so we only had to think about MongoDB. We took all of the application stack except for MongoDB and baked it onto an AMI. So we have the proxy talking to Rabbit, talking to all of the services, and that's then talking to Mongo, and we can just scale this whole thing through one auto-scaling group. There's some upsides to this. It makes it much easier to make decisions about scaling and troubleshooting. It makes it much easier to build and deploy the application. We don't have to care about RabbitMQ as a bottleneck anymore. It gives us coarse control on the whole stack. Basically, we have one big knob on the application. We can turn it up when we need to. Of course, the downside here is we have one big knob on the whole stack. We can only turn it up or turn it down. So could be really easy to be resource inefficient if we don't have the services balanced. Turns out that wasn't too much of a problem, but it was definitely a fear that we had that we'd be really resource inefficient with just one knob on everything. But it made it easier just to focus on MongoDB. So we've taken this here. We've already eliminated a lot of stuff. We've gone to the slice model to be able to just change this into this. We have an auto-scaling group, and we have MongoDB. So we're working on this, and we're also thinking about what are the other parts of the stack that are likely to cause problems. So we had a service as part of one of the services called event log. So we knew from the past this was probably 2/3 of our traffic, where it's just what it sounds like. Events are getting fired. They're being stored in MongoDB, and there's a batch process to go through and scrape and dump these daily and make reports. There are pros here. It's already integrated with clients. They're sending this information. We already have the service. We already have the data. It's already working. But the cons that we saw was this is all going to Mongo. We have one shared Mongo layer. This could be a huge Mongo performance hit. It's going to be really expensive because we're using replication. It's all going through Rabbit, making scaling Rabbit even more of a concern. And it takes a long time to scrape a lot of data. And because it's all part of that stack, all going through RabbitMQ, it has a large halo. If event log is doing bad things to Rabbit or Mongo, it's going to affect all of the services. And we don't want event log to bring down the game backend services. So this is where I'm going to hand off to Evan to talk about how we work together to solve this problem.
So now we're going to talk about the right-hand side. So at this point in time, the WB Play Games team has a lot of problems that they're dealing with. They have a lot of work they have to do. And at this point, mobile game platform isn't even involved. We ended up getting involved in order to help them solve this particular problem. Mobile game platform, we were working within Turbine on a brand new platform that was meant to power our next generation mobile games. This is almost entirely a microservices architecture. It's radically different than what we have today. It's all written in Go. It's all containerized. It's containerized with Docker. It runs on Coreos, which is specialized OS designed just for running containers. And it's built from the ground up to run in AWS. Like I said, it's being written deployed. It's meant to be parallel to the WB game stack. It's not meant to be a full replacement for it. It's all HTTP plus REST. There's no special binary formats here, no proprietary formats. And we were all greenfield. We didn't have the problem the WB Play Games had, where they had a whole bunch of clients already in the wild. They had a lot of APIs that people were already integrating with. They were very, very close to release. And so we had a lot more leeway to do more interesting new things using new practices and new tech. So what do our microservices look like? They're all HTTP plus REST. We spend a lot of time up front developing APIs and sending the API docs off to the game team so they can start to integrate even before we have the service. It also allows us to build prototype services very, very quickly. And since we have an API contract, we know that we can go back later and do some of the scalability concerns and some of the rewriting that we need to do once the game team's fully integrated. They do one thing. They're focused on the code being sane. They're focused on doing exactly what they need. We split up our data store. Rather than having one single MongoDB layer, each microservice, if it stores data, stores its own data. And that data is only accessed through the service's API. We split out all of our configuration. There's no configuration within our service. There's no chef. There's no convergence. At startup, each service will load its config from console. Console is a key value store by a company called HashiCorp that runs and maintains quorum for us on a separate set of machines. We cache all of our configuration at startup. We never change a service once it's running. We've developed a deployment pipeline that allows us to take services down and replace them much quicker, allowing us to much easier reason about what's in production right now, as well as make sure that we don't have configuration mess-ups that take down the whole stack. All of our configuration is encrypted. It's encrypted per service with a brand new key every time we deploy. This makes us much more secure in storing things like SSL keys or database passwords inside our configuration. Like I said, it's all containers. We don't deploy anything that's on a container, even third-party applications. So for our own stuff, because it is written in Go, it allows us to statically compile a vast majority of our services, which means we run from scratch containers. There's no OS in the container. There's no shell. There's no extra libraries. That makes them very, very small. They're about 1 meg on the wire once you compress the container. That means we can deploy very, very quickly because we're not shoving a lot of data around. We use the same containers. We are built for every single commit, for every environment, from the developer's desktops all the way up to production, so we know what we are testing is actually what goes live. We also deploy both our proprietary services and our third-party services in the same way. And I'll talk about that in a couple of minutes. We know exactly what's out there. We deploy by git SHA, which means that we know exactly what commits are in live and exactly which ones are not. This also helps us improve our security. Because we're using from-scratch containers and because we are using services specifically written to run in them, we can drop almost all of our kernel capabilities, meaning we can't change the permissions of files anymore. We can't call chown. We can't do any of the super user things that people worry about when they're running inside containers. So what does this actually look like on AWS? So we run a central, it's what we call a central services cluster. The central services cluster's only job is to maintain quorum and maintain cluster state. This runs console, as I mentioned earlier, which we use for all of our own configuration, as well as our own DNS lookups. It also runs etcd, which is a product by Coreos that overlaps a lot with console and maintains their own cluster state and their own init state. We ended up going with console because it has a lot more features. It has a better API, and it provides DNS access as well as health checks. From there, we have a set of auto-scaling groups. Most things go onto a single auto-scaling group called, in this case, MGP Worker. Our services are multi-tenant, and they coexist with each other. They're all isolated from each other due to the containers. We also have separate auto-scaling groups for really, really big things or really hard to scale things, such as databases, where we want to make sure that we don't end up putting 10 databases on one machine. But even our databases all run inside these containers. In order to do that, we use a system called Sidekicks. Each service isn't aware of its environment. It doesn't understand that it's on. It doesn't understand it's on AWS. It doesn't understand that it's playing in a multi-tenant environment. It doesn't understand how storage works. It doesn't understand anything. Its only job is to serve requests. So we created additional containers that we deploy at the same time that allow the service to get other pieces of resources that it needs. For instance, in this case, we first deploy an EBS sidekick, whose job is to go and acquire our EBS storage, mount it on whatever host we've been deployed on, mount the drive so we can see it, and the service will be able to see its storage. Then we deploy the service comes up, it can see its storage because we provisioned it with the EBS sidekick, and then we attach an ELB sidekick, which allows us to register out with an ELB rather than pre-registering every single instance in the autoscaling group. And then in this case, we deployed a DNS sidekick to register with DNS so we can find it. We use a product called Fleet, which is also by Coreos, to treat our entire cluster as essentially one giant machine, which means that we don't actually know ahead of time where any of our services are going to be deployed. So we use serve records in our DNS sidekick to register every service as it comes up with console so that we can find it, other services can find it as well. This also means that we don't reserve ports for anything, so any service can come up on any port, and the DNS sidekick deals with that as well. So sidekicks are very, very powerful. Some of the other things that we do with sidekicks are we use them to register with other load balancers, things like Vulkan D or HA proxy, Nginx. We can stack sidekicks on top of each other. So we have a single service, but it's registered with two separate ELBs. So we have an internal ELB for internal use, maybe even another account via VPC peering, or we have an ELB sidekick for the public so that clients can hit it directly. We also have sidekicks that register with public DNS via Route 53. And this also works for things we didn't write. For instance, we run Kafka this way. Kafka is inside a container, and it has sidekicks that come up and acquire its storage before starting Kafka. Then we register with an ELB. We even run our databases like this. We can acquire multiple EBS volumes this way, maybe for your journal and for your data. Start our database. We use a lot of Postgres. We also use Mongo, as we mentioned earlier. We kick off SQL migration in a container attached to the database. And then when all of that's done and all of that succeeds, we then register with DNS so that other services that want to talk to the database can actually find it. Because of this, we actually end up treating most of our databases like a microservice unto themselves. Our deployment system sees a database as a separate service and knows how to deploy it separately. So now that we've talked about what we actually do, let's talk about how we were able to help with this particular launch. So we ended up building a service called Event Ingestion to replace Event Log. It's the first service that the team ever released. Like I said, we were doing mostly research and greenfield work for upcoming games. So this was going to be the first thing that we were ever going to release to the public. Clients send events directly to this service. That's why there's the split that you saw earlier. The service sends all that data into Kafka. And the analytics team can consume directly from Kafka as fast as they want or as fast as they can. So why is this good? It lets us scale completely independently. We didn't have to worry about what the WB game stack was doing, if it was having problems, or what our scaling would do to their stack. It supports real-time analytics. This was kind of an extra bonus, but because we're sending everything into Kafka in real time, the analytics team can use things like Spark to pull the data off Kafka at their leisure. And it's completely isolated. So the cons is I had to go out to all these game teams and convince them that 2 months before launch, they should rip out an integration they had and do it my way instead. This is pretty hard when you have game teams struggling for launch because they don't care about my problems. And I had to go to multiple studios, doing multiple ports, multiple teams, but ultimately we were able to convince them. So what does the traffic actually look like? We come in through the ELB, we talk to event ingestion, and then we go over the VPC peering link we showed you earlier and to talk to Kafka. We also have what we call a schema service. The schema service holds, in our case, Avro schemas, which is a way that we can have the game teams publish what their events look like ahead of time, so that once it gets to analytics, they don't have to infer what all of the events mean and what all the data types are. We've already told them.
And then one thing to note here, too, is that the actual event traffic from event ingestion into Kafka doesn't actually go through the ELB. One of the common problems we see a lot on the Kafka user mailing list is running on Amazon when you have private and public networks. And it can be it doesn't handle the multi-addresses very well. So one thing we were able to do is it registers with an ELB. The Kafka clients, by default, will reach out, talk to whatever connection string you give it to just query for the broker list. So you can set up a Route 53 DNS alias just to talk to the ELB to get your list of brokers. And as we register everything then on the private IPs, everything can talk over the VPC peering links. And sort of ease that service discovery a lot. So we have one connection string. We can change out Kafka hosts underneath the hood, and neither any of the event ingestion environments or any of the analytics team environments actually need to know about it, which is something that was traditionally a little harder with Kafka and was helpful having the MGP Sidekicks system to sort of make that simple.
So we were able to scale this up pretty rapidly. We tested it up to about 200,000 requests a second at 250 byte messages. Each request had about 1 to 6 messages in it. Most of them were on the small side. We can do that on about 15 C4 larges at 75% CPU. And this includes verifying that the data is coming in is for a valid schema. That allows us to reject a bunch of data that malformed clients are sending or maybe bad actors are sending right away. On the Kafka side, that translates to about 250,000 messages a second. We set up as 20 partitions per topic with a replication factor of 2. That means every piece of data that comes in is on at least 2 Kafka brokers. In this set, we only use about 6 brokers, and they're only R3X larges, and they only have a single 10 terabyte GP2 volume. Thankfully, AWS released the large volumes literally the day we had to set this up, because we were not looking forward to managing 10 1 terabyte GP2 volumes on every single broker. This is a pretty small footprint. Kafka is used by all of the games. It's used by analytics as well. It's used in some cases to self from the analytics stack to publish stuff for the other pieces of the analytics stack. And with this method, we believe we can just add more brokers, even at the small size, and get at least 1 million messages per second before we have to look at either scaling up the brokers or potentially scaling up any of the storage. So side by side, we have both of our platforms up at this point. We've got most of our data going in through event ingestion now. We've got about 2/3 of our data going through there, which for us is about 2 billion requests a day. So it's not a trivial amount of data. It's not a trivial number of requests. And we've saved the other stack, which is doing a lot more logic and has a lot more to deal with due to the storage and all of the other things it's going to do. We've taken all of that load off it, and we've moved it all over to event ingestion without ever affecting the WB Play Games team. They were barely involved in this particular transition because they were dealing with a lot of other things, such as launch time.
So we've got this stuff in place, and we're ready to launch. And so we're doing a midnight release, and we're figured, midnight release, can't be that many people who are going to be sitting there at midnight just waiting for the game to come out. Turns out, we actually couldn't find the graphs, but it's pretty cool because you can see the unlocks coming across Europe, and then US East hit, and all of the traffic hit exactly at midnight. Our new players per second right here jumped up to its highest number ever and just continued along. We went from like 100 requests a second to 60,000 requests a second in a matter of minutes, and then it just never stopped. So for context, this is new players per second right at midnight, and then now, a couple weeks after launch, it's settled down to like a much order of magnitude lower number. Pretty interesting. So this was pretty interesting. We'd load tested. We were ready to handle a certain request rate in Mongo, and we immediately had to start scaling it up. So I'm going to talk through 3 challenges we had right at launch with MongoDB, scaling that up. One of the first things was our Oplog data was through the roof. So the Mongo Oplog stores all of the operations that modify the database. If you're modifying the database a lot, you get a lot of Oplog data. We're also getting read queues that were backing up the services. Mongo is writers block readers, so it's an in-memory latch. When you take the write lock, readers are blocked until the lock is done. So we were getting a lot of block reads from write locks. We'll talk about that. And then eventually we started getting these frequent MongoDB failovers that we had to deal with. So first, the Oplog data. Well, actually, first the architecture. So a standard replicated sharded Mongo setup. We're doing a 3-node sharded replicated set. We have a primary replica and 2 secondary replicas that can fail over, and primary can move around. The data volumes we were using are GP2. We had pretty large volumes, so the IOPS we got from just the size of the volumes we needed for GP2 was enough for I/O throughput. We're a little behind. We're using Mongo 269, but worked. We started out with R3 2XLs using 2 terabyte GP2 volumes. The 2 terabyte GP2 volumes will give you 6,000 IOPS, no burst, just baseline. And we were in 3 AZs for high availability. And we started with 6 shards. So the Oplog data, we're at 6 shards at launch. We get all this traffic, and we're seeing up to 100 gigabyte per hour in Oplog per shard. That's a lot of data every day, to be able to take that and use that for backup. And it basically meant we were unable to use off-the-shelf backup solutions. We needed to solve this problem right away. So we did a deep dive into what was going on, why the Oplog data was so high. And what we found is we had some server-side bugs and some client-side patches that we needed to get out, where on the server side, we were writing and reading way too much data. We were writing full documents every time, and we just went in and worked on a patch for that. And also, on different platforms, different clients were sending updates much more frequently. So we had some really chatty clients that were sending updates really often. And we were actually able to get that with a patch out to one of the clients that turned down the update rate by about a factor of 20. And we also were expecting diffs, and some of the clients were sending full documents instead of diffs, so we were writing all the keys every time. So we fixed the bug on the server side, got patches out on the client side, and reduced the Oplog rate from 100 gigabytes per hour down to about a gigabyte per hour, which is much more manageable, and we were able to use off-the-shelf backup solutions at that point. So we got that out of the way, feeling pretty good. And I'm going to go through the timeline of the other 2 challenges. So this diagram here is sort of showing our scaling timeline over time. You can see at the bottom is sort of a representative measure, subjective measure of stability over time, where over time we're doing things and we're gaining more and more stability, but we're not fully stable until we get to the end. At the top, it's showing the footprint of the Mongo environment and telling you how many shards and instance types we had for that footprint. So for example, 6 shards at R3 8XL towards the left is the same footprint as 24 shards at R3 2XL in terms of the amount of resources using in Amazon. So over time, we're scaling up. We're going from 2XLs to 4XLs to 8XLs. Then we're adding shards. We're adding more shards, and then we start scaling down over time to go from 8XLs to 4XLs to 2XLs. I'm going to focus on the write lock problems first. That was the second problem we had here. And while we were working through this problem, this is where we initially started scaling up and then scaling out, where we went from 2XLs to 4XLs to 8XLs, and then out to 12 shards, and then eventually out to 24 shards. So what were we seeing? We were seeing huge spikes in queued operations, 10, 20,000 reads. And we weren't doing anything really that unusual with Mongo. We're primarily read operations, order of magnitude more reads for every write. And we had a relatively low lock percentage under normal load. We're 20, 30%. This should be fine. This shouldn't be a problem for Mongo. We didn't understand why we were getting these read queue backlogs. If you look at this, we're doing about 80,000 reads per second at the database. We're only doing 3,000 writes per second on the database. But the writes are huge. They're 50 to 100K documents that we're putting into the database. So we're seeing 20% lock on average. I/O is fine. But we're getting these massive spikes up to 20,000 queued reads, which were just tanking the application. So we spent a lot of time with my new favorite tool, mplot queries, and Mongo log analysis. What I'm showing you here is this is the cumulative distribution function for the write locks that we were looking at. So what we did here is we took the Mongo logs, we set it to log level 1 so we could get a write lock time for all of the locks over a 5-minute period, and then threw it into some analysis tools and took a look at this. The x-axis is the cumulative frequency, so you go from 0 probability to 1 probability of seeing this write lock time. The y-axis is the write lock time in microseconds. For people familiar with Mongo, this scale is kind of insane because it goes up to 10 milliseconds. What you can see here is at the very lower left corner, we have a sort of standard write lock of like tens to hundreds of microseconds. It immediately jumps up to hundreds of microseconds. And then by the time you get to the 95th percentile, we're having 1 in 20 requests, 1 in 20 updates taking more than 2 milliseconds to write to the database. So we have a lot of requests that are taking a long time to write, and that's meaning that our updates per shard were way lower than you would expect for the update rate we were getting. So that's when we started sharding out horizontally when we saw this. We doubled the number of shards once, then doubled the number of shards again to get the updates per shard down to something that could be handled with write locks this long. So to summarize, what was going on? We had very long write locks, which were increasing the impact of low lock percentage. We also found another thing where we were using a relatively old Linux kernel, and it turns out it had a problem where it did a lot of context switches, and they were also slow context switches. So we were actually just able to change the Linux kernel to a newer Linux kernel, 3.14, and that actually halved the number of context switches and reduced the write lock time by about 40%. And then we also doubled the number of shards. One of the things we ran into here is because the documents we were seeing were much larger than what we expected and thought would ever go in, where like documents were moving. Mongo uses a power of 2 padding to allocate space, but if you exceed that padding, it has to find a new location to write the document into the database. It has to move it. It takes a long time to do that. So we've sharded out to handle the long write locks that we're seeing. So we're focusing on this second part of the stability over time timeline that we have, where now we've got 24 shards. They're 8XLs. For context, those are 3 node replica sets. That's 72 R3 8XLs. If you do the math, that's about 18 terabytes of RAM. It's only 6 terabytes of RAM for the active working set, but that actually wasn't enough to keep all of the working set in memory. So we're looking at this. We think we're going to be stable now, but we're in this zone here where we have a ton of nodes, a ton of memory, and we start seeing the primaries fail over every now and then. No good reason to explain it. We spent a lot of time investigating it. And we're looking at this mystery where we have these symptoms. We're seeing spikes in system CPU. We're seeing the MongoDB process stall. It's never good when you see a process at 9999% CPU for 2 minutes. If you have a process that's at 9999 CPU for a couple minutes and it's in a quorum system, it triggers an election because it wasn't able to respond to heartbeats, and it basically showed up as a network partition to the replica set members. While this is happening, we have 2 minutes where the process is stalled, it's failing over. This is causing the application to backlog. It's got a queue of work waiting to come in, so as soon as a failover happens, we immediately swamp the system by trying to flush out the backlog of work that's just waiting for this to happen. Not particularly fun. What was going on? Our hypothesis was too much RAM. Basically, we spent a lot of time looking at this and looking at the kernel source, calling everyone, reading through everything, looking at the compact stall statistics in the kernel, and basically, with the amount of RAM we had, the memory compaction to satisfy allocations was just taking a really long time and causing the process to stall while that's happening. So what did we do? We went to smaller instances. We gave ourselves less RAM. It's really hard to convince yourself when you're having problems with the database that less memory is going to help. But this did it. We went to 4XLs, started getting better. We went to 2XLs, got rid of the process stalls. We could still see the spikes in system CPU, and we still have the same symptoms, but they're smaller and faster and not causing the problems. So we just scaled out widely with smaller instances. So we've gone through this long process. We're working through all of these things. We're adding stability over time. Eventually, we ended up at 24 shards, R3 2XLs, and it's pretty good now. Side note for Python and SciPy fans, really easy to make CDFs, super useful to try and understand bottlenecks in your system. This is just an example of the code we were using to make that type of graph where it's really easy. Grab NumPy, pull out the write locks with some awk, grep, whatever you want. Make the histogram, do a cumulative sum over the bins, plot it, and you'll get a really good idea of what the distribution of what you're looking at is. Really easy. We're working on Mongo, but we're also trying to solve other problems. So I'm going to hand off to Romy to talk about some of the other things we're doing.
So during this entire troubleshooting process with Mongo, the game was up. I mean, we couldn't take it down. So we needed to figure out something that would help us kind of control what was coming in. We need to be able to buy some time to solve some of the back-end issues that we saw. We needed time to look at our Oplog data. We need to take some of the load off the system as well. As I said, the game was live. We couldn't pull it. So we started looking through and trying to find which specific calls were actually causing problems. Turned out we actually managed to find a handful of calls that were actually pretty low value to the client, but surprising impact on the back end. So we needed some way that we could kind of configure this on the fly to say maybe this one call that's maybe populating this one little widget can go down to little or no traffic, while this platform maybe is really important right now and we really want to let everything through. So Nginx. It seems silly, but it let us do everything we needed to do. It let us cache calls that were kind of uncacheable. So if people are familiar using either CDNs or Varnish, kind of can't cache posts that are getting data. Turns out we had some. It was really important for us to be able to return them from the very front of our application stack before it ever got anywhere else. It also has a really good built-in rate limiting engine. So we could actually pick individual endpoints, platform keys, whatever we needed to do, and apply a rate limit across the farm specifically to those calls to allow a little bit of pressure to get relieved on some other ones. Additionally, since we had the MGP stack running, we had console. So I don't know if people are familiar with conf d. It's a little tool that Kelsey Hightower from Coreos wrote. Basically, it's a templating language that will pull keys from console, either on a schedule or just a key watch. And as you change them in the key value store, it will just automatically either restart your application or run a series of commands that you specify. So that let us manage all of our, so we could horizontally scale our Nginx farm and then manage our config centrally, which would then allow us to quickly iterate on these rules and test hypotheses and check our metrics. So the first thing we really focused on, caching. This is something specific, I think, in the kind of the gaming industry to us, is we're talking to a number of game teams, and we discovered very different definitions of what real time meant. We're an MMO company, so real time means like you do it, you see it right away. After launch, we realized that maybe real time meant more like somebody in customer service needed to update a post, and real time was really like 5 minutes, which is a very different problem set that we had to solve. And so we actually managed to identify just 2 endpoints that saved 50% of our traffic back to the actual application stack, and that actually made everything way better. So on the left, you can see the Mongo lock percentage, already relatively low, but still really spiky and kind of weird. Even that out. Our ELB latency, that's insane. It should never go up to 4 seconds. So, and we were just seeing these odd spikes that once we actually just buffered everything up front, it allowed us to actually smooth everything out, and then as well as just establish TCP connections. We were holding 1 million connections open, hundreds of thousands of connections open, kind of for no reason. So just a couple of high impact calls really, really gave us the time to actually, solve what we need on the back end. Also, a couple of problems. I'm personally very used to caching with Varnish, using a CDN, very much in memory. Part of what makes Nginx awesome is that it has a great way to handle static files, and it turns out the caching engine leverages that same technology underneath. Plus, we also had huge requests, 50 to 100K writes. None of the defaults are really particularly good for that, and we'll actually write extra temporary files. And additionally, we're caching too much. A number of those calls maybe only got accessed a couple of times, but we had enough players that maybe mattered. So the caching engine has the proxy min uses config value, so I think we settled around 5. So once something had been cached 5 times, then had been requested 5 times, then we'd actually hold on to it. Problem before we actually configured all this is that we were using relatively small EBS root volumes, so I wasn't expecting our disk to be a bottleneck for caching. Turned out that we were improperly configured, so it was actually a problem, and we maybe went down at maybe 3 o'clock in the morning. Maybe called a lot of people. And also, unexpected disk usage. It wrote out millions of temporary files, and the default ext4 inode settings are pretty small. So between those 2 things, we used up all the burst credits on our GPU volumes, and then we ran out of inodes once we got through that. But a couple of config tweaks, and then being able to just scale out and change the infrastructure that we're running on Then we're actually pretty good, and we're running pretty steady state, and that's really where a lot of those smoothed out graphs came from. And so I'm going to hand back over to Will to talk about actually throttling the traffic.
So part of what we were doing with the selective degradation was throttling some of the endpoints for different platforms, or the low value but high impact queries. So we went through our logs and focused on the highest impact calls first. Again, we went through, used mplot queries to find we had some poorly indexed queries. We also had the really chatty writes. And with the write lock problems we were having, these chatty writes were blocking reads. So we used throttling to be able to tune down the number of writes we were accepting, to let through the reads and let the backlogs come through. And then we just blocked some calls. We had some calls that we could just block, and the game would be not totally complete, but it would work. We used a lot of the instrumentation for this because we had instrumented all the things. We were able to look through and see what the call rates were for all of the endpoints, see how frequent they were used and by platform. And so with those detailed metrics, we were able to go through and say, who's using what, how often are they using it, what are the writes we're getting from that, and use that to build some, how we would throttle the things that we needed to and let the reads through that we wanted to get through. This is no panacea. We have different clients behave in different ways, and we're trying to balance all of this so we can buy time to scale up how we need to scale up. One of the problems we ran into is, you're essentially applying your probability of success to the endpoint that you're throttling. Well, if you have multi-step flows, so a client is doing multi-step auth and you are throttling auth, that probability gets multiplied out. So multi-step auth was failing more often than you would expect from what you were throttling at. Also, retries. Retries are a thing. We throttled some endpoints, and then clients immediately tried as fast as they could to get back into the endpoint, which was not particularly great. And some clients actually would see one failure at an endpoint and assume the whole game was offline. So we really had to balance what we were throttling with how the different clients handle those endpoints being throttled. So we learned a lot of stuff. This is a lot of experience really fast. One of the key sort of takeaways that I got from this is it's very easy to have metric overload. So we had measured everything, we were graphing everything, but don't display graphs unless there's a problem, or someone will find one. Because you look at them, we eventually summarized this as measure everything, mysteries everywhere. Because you're going to have outliers, because the internet. And just don't stare at graphs all day. It's very easy to do that. Just build a process, have your baselines, be able to measure everything, and then show important things, and use alerts to drive when you actually want to look at your graphs and not just stare at them all night going, is this the internet or is this us? So I'm going to hand back off to Evan to talk about some of the other things.
So this wasn't a game that we got to soft launch. We went literally in minutes to our peak request that we would ever see. When we talk about going to 3 billion requests, we handled 3 billion requests the first day we were out, right? And we never got as big or as spiky as we did that first day. Unfortunately, that meant that some of the problems that we had, we couldn't pivot as quickly or know as much as we wanted to ahead of time. So if you can, soft launch, figure out what's out there, build your baselines, figure out what your metrics actually mean. We definitely had some metrics that we didn't know how they related to the actual health of the stack, the actual health that the clients were actually seeing. Test and validate your metrics, and confirm your graphs mean what you think they mean. Your real players will create real data. We did a lot of load testing, and we did a lot of theoretical testing, but it turns out there were some fairly big holes. We had no idea how big some of the requests were going to end up being. For instance, we had no idea what certain call patterns were going to emerge. Flexible APIs, they let your clients do really flexible things. We had clients that, like we said earlier, were sending really big writes, clients that were doing things really fast or not backing off when they saw errors. So make sure you keep on top of what's actually happening. And look at your soft launch data and usage patterns. And some of the stuff that we had to learn during our launch window, we could have learned earlier. Don't forget your blast radius scales too. If you're using other vendors, and you almost definitely are if you're going to launch a large-scale game, make sure you let them know what you're doing. We had a case with Labrada. We were using a beta, some of their beta stuff, and we actually managed to create a graph that broke them. They were able to pivot really fast, and it didn't they never stopped accepting metrics or anything like that. But the only reason this was really bad is we had forgotten to tell them who to contact when we did this. So make sure you have your other internal team contacts too. You might think you're not affecting them, but there's a good chance you are. Let everybody know before something big happens. Remember, your blast radius is more than you. You can easily take down other third parties, other teams, other games, other services in your own platform. Pick your battles. Solve your biggest problem first. Even if there's other things that look like they're low-hanging fruit, you will waste time trying to pick up things that aren't actually helping you. Use AWS scalability to buy time. You can trade money for stability for a short period of time for a lot of things. Make sure you have someone dedicated to triage. With so many people and so many teams, none of the teams were actually talking to each other because they're not in the same building. So one team would see a problem and they would talk to us on HipChat, and people would jump in and try to help because people are helpful, but it took people away from the important problems. You don't need to rewrite everything. One of the big things we found here is the mobile game platform team was able to peel off and do a huge amount of work that saved a lot of trouble without having to fully understand everything the other team was doing, and without having to rewrite everything that they had to do literally weeks before launch. Share your APIs, not your data. This helped us a lot because we were able to isolate our data over to the side and allow other services and other teams to get at our data in a sane way. So what's the future? We're going to do more of this. As new features are required, as new services are required, we're going to break them off into the more microservice type platform. We're going to continue to embrace immutability. We talked earlier about we don't reconfigure services on the fly. We don't reconfigure instances on the fly. We're going to keep going down that path to make sure that we can destroy instances or destroy and recreate instances environments without having any knowledge of what they're currently doing. More cross-team collaboration. This is really hard sometimes in a big company. You tend to get siloed. There's a lot of people out there that even if they don't look like they're doing what you're doing, they probably have a lot of really good knowledge for it. More Amazon support. Our solutions architect is in here somewhere. He talked just before this. Our Amazon support team actually came in for this launch and sat with us on site in our war room for 48 straight hours through this launch. And where I was hiring, not only for this, but also for the game teams, everything, come work for us. So this takes a ton of people. It's certainly not just us, but thanks to everybody inside Turbine, all of our vendors, Amazon, everyone who lets us do this. And yeah, that's about it, guys. Thanks.